Over the last decade, we have experienced complementary growth of information technology and electronics. And that's why in our group, we are advancing the field of state-of-the-art electronics by strengthening its existing capabilities as well as adding new functionalities to them. At the same time, we are conceptualizing as well as realizing futuristic electronics to meet the demand for next generation. And finally, we are relentlessly chasing our passion to discover new application areas for electronics. Electronics is a very multidisciplinary field. We need to know math, physics, chemistry, and today we also need to know biology, because nature-inspired electronics are gaining popularity not because that they sound catchy, but they are also important. We need to learn from our nature, and as well as biology is the vehicle for them. So to pursue our research, we are transforming either the material properties, the structure, the device geometry and architecture, as well as the substrate, and often we even look into the waste materials and transform them into something which is valuable for us. So as we know, electronics today, 90% of them, 90 to 95% of them are made using ultra-thin mono or polycrystalline thin film based material system. At the same time, there is a rising kind of electronics which are based on organic chemicals or molecular electronics. The question is there a way that we can do hybrid integration to bring them on the same platform, or if there is a way that we can transform the traditional ultra-thin film based electronics into doing exactly the same thing that those organic or molecular electronics that they can provide in context of their flexibility, stretchability, shape changing, reconfiguration, all sort of different things which most probably are mainly available in our biological systems. So that's exactly what we do. But we do make sure that we don't compromise on the high performance, means the data processing speed, like basically also the energy efficiency, means like that we can make them portable, they are ultra mobile. At the same time, not only that, their cost effectiveness and ultra large scale integration density, which is basically allows us to have more functionality in devices like iPhones or like the smartphones or tablets or somewhere else. So basically keeping them as they are, and if we can add more functionalities, that's exactly what we do using CMOS compatible processes. And to do so, we also engineer the material. We try to understand how different material sets work out. We apply various kinds of chemical processes to bring them cohesively, performing the integration between new kinds of devices and then eventually for systems, for applications which were unimaginable in the past. I joined academia to pursue one of my critical passions, and that is to discover and to explore new ideas every day. And KAUST is actually enabling me to pursue my dream to come up with ideas and to impact the broader mankind. Just imagine that every single day my group and I'm working towards one future world, the world where every objects surrounding us are going to be interactive to us. They are going to be making our life more convenient, more comfortable. Our healthcare is going to be much more advanced and simplistic, more economical. We are going to be in the transportation system, which are going to be very extremely interactive and will provide us with a safe and secure commutation. Not only that, there are so many different areas that we can work on, which was never been actually thought of or which was never been imagined. So what we are doing right now, we are taking the electronics, making them much better, making them something which were not that in the past possible, and coming up with ideas and applications which are focusing on the smart living as well as for sustainable future. And that's just to create a better world for ourselves as well as for our future generations.
My research project is in the field of energy storage with a focus on the fabrication and characterization of flexible lithium-ion batteries. We are developing the next generation of micropower sources as part of the smart city concept. In a smart city, you can think of every product from cars to traffic lights, from smartphones to PCs, and from washing machines to even our clothes as being intelligent. All of these products need to talk to each other. This is why we can see that embedded energy storage is an absolute requirement. In our lab, we are developing an all-solid-state lithium-ion battery which is flexible and also has small footprint. It is eco-friendly since it contains no toxic chemicals. It has high energy density thanks to the high-performance lithium metal cobalt oxide, and it can withstand the lifetime of the product since it can be cycled thousands of times.
My research work has been divided into two main topics. First, I have been working to develop a process that allows us to peel a very thin layer of silicon with the state-of-the-art electronic devices on it. Now, this is a very exciting development because first, it relies only on the standard microfabrication techniques and the very cheap silicon substrate that has been used in the industry for over 5 decades. Second, it actually allows us to develop devices that are not only ultra-fast, multifunctional, and also energy efficient, but also to be mechanically flexible and adaptable. Now, the application then can be in areas such as wearable electronics, three-dimensional integrated circuits, or in bionic or bio-integrated electronics. Now, my second research topic is about energy. So, how we can make use of microfabrication techniques and nano-engineered materials to produce clean energy in an efficient and self-sustainable way. So, I have been mainly focusing on micro-sized microbial fuel cells, which are basically tiny generators that are able to harvest energy out of bacteria decomposing their organic waste and out of water. So in that case, we're actually able to treat the water and to produce electricity at the same time. Now, we have developed several kinds of micro-sized microbial fuel cells with diverse techniques, architectures, and with novel nanomaterials such as carbon nanotubes and graphene. And with this, we have been able to improve the power generation, optimize sustainability, and also to reduce costs.
In my opinion, CAUS is a unique place since it has high-end facilities to be accessed not only by researchers but also graduate students.
So to me, CAUS is an extraordinary institution which is rapidly growing, very research-driven, and with a unique multicultural